From that sharp tang you get from vinegar to the sweet smell of a pear, the chemistry of carboxylic acids and esters, well, it's pretty much everywhere. So, over the next few minutes, we're going to break down exactly how they're built, how they react, and crucially, how to name them. Basically, everything you need to ace that exam. All right, let's dive in.
So here's the plan. We'll start by getting to know our main player, the carboxylic acid. Then we'll check out its origin story, how we actually make it from an alcohol. The real excitement happens when we mix the two in a reaction called esterification. And to wrap it up, we'll see how these new things, esters, get their names and those famous fruity smells. It's the whole journey, from acid to aroma.
Okay, first things first. Let's meet the star of our show, the carboxylic acid. And to keep things really clear, we're going to focus on one key example, ethanoic acid.
So what are they? Well, carboxylic acids are a homologous series. Think of it like a family of compounds that all have the same general formula and kind of similar chemical personalities. And their main family trait? It's this super important functional group, the carboxyl group, which we write as RCOOH.
Let's zoom right in on that carboxylic group. Honestly, you've just got to have this structure memorized. It's non-negotiable. You've got a central carbon that's double bonded to one oxygen and then single bonded to a hydroxyl or OH group. This very specific arrangement is the key to, well, all of its chemical behavior.
So our go-to example is going to be ethanoic acid. The F part of the name tells us it has 2 carbons in total. One is in the methyl group, and the other is right there in the carboxyl group itself. And you definitely know this molecule. It's the acid that gives vinegar its sharp kick.
Now here is an absolutely critical point that trips a lot of people up. Even though they've got acid in the name, carboxylic acids are weak acids. You can't put them in the same category as strong lab acids like hydrochloric acid. This difference is fundamental, and it totally changes how they act in water.
And this table shows you exactly what we mean by weak. A strong acid like HCl, it just completely falls apart in water. But look at ethanoic acid, it only partially dissociates. And the dead giveaway, it's this reversible arrow. That symbol is screaming equilibrium at you. It means most of the acid molecules are just hanging out, staying whole. And that is the signature of a weak acid.
But hey, being weak doesn't mean they're boring. They still do the 3 classic acid reactions. And for your exam, you really need to know this playbook by heart.
First up, they react with reactive metals like magnesium. This kicks out a salt and hydrogen gas, which you'd see as fizzing, or effervescence. And take a look at the salt's formula. Magnesium forms a 2+ ion, right? So it needs 2 of those ethanoid ions to balance out the charge.
Next is the reaction with a base like sodium hydroxide. This is just a classic neutralization. The acid and base get together to make a salt, in this case sodium ethanoate, and water. What's important here? As you can see from the equation, there's no gas, so no fizzing.
And finally, the big one, the reaction with carbonates. This is the definitive test for an acid. Why? Because while only some metals will fizz, any carbonate will go nuts with an acid, producing a ton of carbon dioxide gas. That flood of bubbles is your unmistakable proof that you've got an acid.
Okay, so we know how ethanoic acid behaves, but where does it actually come from? Well, that brings us to its origin story, how we make our acid from a simple alcohol.
We make ethanoic acid by oxidizing ethanol, and there are basically 2 ways to do it. You've got the fast, controlled chemical method we use in the lab, and then there's the slow, natural microbial way that happens all around us.
For the lab method, these right here are the details that get you the marks. You need a powerful oxidizing agent like acidified potassium manganate 7. You have to heat it under reflux. That's to stop all your volatile stuff from just evaporating away. And the key observation? The deep purple solution turns completely colorless when the reaction is done.
The other method is probably way more familiar. It's literally what happens when you leave a bottle of wine open. Little bacteria floating around in the air called acetobacter use oxygen to slowly oxidize the ethanol. And the result? Your wine turns into vinegar. That's microbial oxidation happening right there in your kitchen.
All right, let's get into the technical core of this explainer, esterification. This is where we take our carboxylic acid and react it with an alcohol to create a whole new family of compounds called esters.
Now, to get this reaction going at a decent pace, we need to mix our acid and alcohol, add just a few drops of concentrated sulfuric acid to act as a catalyst, and then gently heat the whole mixture. What do we get at the end? Our ester plus a molecule of water. So chemically, this is called a condensation reaction. That just means 2 molecules join up by kicking out a small molecule.
In this case, water. I like to think of it as a snap reaction. Imagine two Lego bricks, but to get them to click together, you first have to break a tiny little piece off of each one.
Okay, this is probably the most important detail of the whole mechanism. Where does that water molecule come from? Pay close attention here. The entire OH group is lost from the acid, but from the alcohol, it's just the single hydrogen from its OH group. Getting this detail right is absolutely essential.
So once that water molecule is gone, the two leftover fragments are ready to connect. They just snap together, forming this new bond, the characteristic ester link, COO.
So we've made an ester. Great. Now we just need to figure out what to call the thing and, what it's actually used for.
Naming esters. I know, it can feel a little backwards at first, but there's a simple two-part rule. First, you name the part that came from the alcohol. That's the chunk attached to the single bonded oxygen, and you just change its ending to -ile. Then you name the part from the acid, the section with the carbon-oxygen double bond, and you change its ending to -ote.
Let's try that rule right now. Our alcohol was ethanol, so that becomes the first part of the name, ethyl. Our acid was ethanoic acid, so that becomes the second part, ethanoid. Just put it together, ethyl ethanoid. See? It's a simple and super reliable system once you get the hang of it.
So what's the big deal about esters anyway? Well, they are basically the molecules of smell and flavor. They're what give fruits and flowers their amazing scents. And because they're volatile, which just means they evaporate easily so they can get up our noses, they are perfect for things like perfumes, food flavorings, and even as industrial solvents.